Well, it really is wonderful to see so many great friends of Berkeley Optometry and Vision Science here in the audience. We're gathered here this evening to celebrate a monumental moment in our nearly 100-year history at the University of California, Berkeley. Under the leadership of Dr. Herbie and Mrs. Nicole Wertheim, the Herbert and Nicole Wertheim Family Foundation has committed to contribute a $50 million gift to UC Berkeley's Herbert Wertheim School of Optometry and Vision Science. This transformational gift is the largest to any school of optometry in North America, and we believe the world. This gift is also the cornerstone of a $100 million investment in the Herbert Wertheim School of Optometry and Vision Science over the next 10 years, of which over $75 million has already been committed. The Wertheim's gift will ensure that Berkeley Optometry will be prepared to lead the profession into its next 100 years. Optometry as a primary healthcare profession is stronger than ever, and this gift will ensure that the Herbert Wertheim School of Optometry and Vision Science will lead the profession into its new and essential future. In celebrating our gift, we also celebrate the philanthropic philosophy of our benefactor to fund public universities and promote access to public education, to promote public and global health and access to primary care, and in so doing, making life better on Earth. Herbie will tell you that the three pillars of primary care are prevention, diagnostics, and remediation. You see, I've listened, Herbie, in all of their forms. Your belief in these principles and actions were rewarded yesterday evening, Herbie, by a Chancellor's citation, an acknowledgement of your extraordinary commitment and philanthropy. The gift will support new clinical and educational facilities, the expansion of the school's clinical network and residency training, a focus on new initiatives for children's vision, the creation of endowed support for both professional and research graduate students, and a new Vision Science Institute to help unite the vision research at UC Berkeley. These initiatives will be supported by the creation of two new endowed Chancellor's chairs, the Herbert Wertheim Chair in Neurooptometry and the Nicole Wertheim Chair in Pediatric Optometry. It is particularly fitting, given the gift's emphasis on excellence in pediatric eye care and vision, that this weekend's Golden Conference was on the topic of children's vision, bringing together some of the country's brightest and best in pediatric optometry. Most of the speakers are with us here this evening. Thank you for sharing your talents, and in particular, a warm Cal welcome to Dr. Susan Cotter, the President-elect of the American Academy of Optometry. Welcome, Susan. Where are you? There you are. Our celebration marks both a milestone and a tipping point in our school's and our profession's history, one that has come about by the convergence of our extraordinary past achievements and enabled by the Wertheim's Foundation's equally extraordinary vision for our joint future and the promise of an even greater future successes. We warmly and enthusiastically welcome the Wertheim Family Foundation as partners, collaborators, and stakeholders at the school and the university. On a personal note, it's been a truly inspirational journey getting to know Herbie over the last 4 years. He will tell you proudly that he's one tough negotiator. Hopefully, I'm learning from one of the best. But we have developed a friendship and respect that makes our partnership strong and special as we move forward in this exciting adventure. I'm also delighted to have met Herbie and Nicole's daughter, Vanessa, and look forward to future work together. All of us in optometry and vision science are privileged to work with the Foundation towards a common purpose that both honors Dr. Herbie Wertheim and his extraordinary life and improves the lives of countless people and communities in a meaningful and sustainable way for generations to come. Our celebration would not be complete, however, without acknowledging the unwavering support of Chancellor Christ. Chancellor, yes, I think that's appropriate. Chancellor Chris, will you please come to the podium and address the audience?
Thank you, John. What a wonderful evening. It's a pleasure to be here to celebrate the naming of the Herbert Wertheim School of Optometry and Vision Science. This extraordinary $50 million commitment from Dr. Herbert and Mrs. Nicole Wertheim lays the foundation for a new era at Berkeley and beyond. Beyond. Because this investment will have ripple effects from the students, physicians, and scientists we train and the discoveries they make to the communities we serve, especially those that need our services the most, including children and those who cannot afford or have limited access to vision care. Ultimately, this gift makes a generous and strong statement about broadening the scope and impact of optometry and vision science for the benefit of humanity. And it builds on a presence that's already significant. Our eye clinics have 200,000 patient visits a year at 66 clinics, including 2 campus clinics, 10 satellite clinics, 6 federally qualified health centers, 7 VA clinics, 24 external training clinics across the country, and 17 on-site specialty care clinics. Our vision science research program encompasses faculty not just in optometry, but in a total of 9 different departments across campus. The 19 dedicated faculty in optometry account for 0.009% of the total faculty on campus, yet generate 5% of the campus's research funding. These are just some of the indicators. Yeah, that's a great statistic. These are just some of the indicators of our current scope, the foundation which this gift builds upon. And this landmark commitment of $50 million is just the beginning. It seeds a bigger campaign for optometry and vision science that we're excited to kick off tonight. Our goal is to double the impact of this gift and to raise a total investment of $100 million. I hope you'll find this challenge and the opportunities that will follow just as exciting as I do. And this new partnership with Herbie and Nicole Wertheim is a natural fit for us. Herbie Wertheim's life mirrors achievement and service. From his humble beginnings as a high school dropout in Florida who liked frogs and snakes, he built a career that has included serving as an engineer at NASA, working with the team that launched America's first foray into space, and teaching and leading academic institutions and creating technologies that have saved countless people from debilitating eye disease. More than 40 years ago, through his own clinical practice, Dr. Wertheim discovered the dangers of ultraviolet and blue light and developed products that have helped prevent cataract and macular degeneration for countless numbers of people. Throughout his extraordinary life, Dr. Wertheim has been engaged and interested in the role that good vision can play in cultivating a life well lived. Recognizing that healthy eyes are critical for success inside and outside the classroom, he and Nicole designated a portion of their gift to support pediatric eye care. Their interest in supporting healthy vision in young people is motivated by their experience as parents, as well as in Herbie's work as a clinician. This gift includes funds to support a pediatric eye care model clinic at Berkeley, as well as the establishment of Berkeley Vision Cure, a national and international initiative that aims to provide eyeglasses to every child in need of them. The endowed Nicole Wertheim Chancellor's Chair in Pediatric Optometry will ensure that a top faculty member has the resources they need to pursue research in this critical area. Herbie's career has always been grounded in a sense of duty to the greater good. He and Nicole have emphasized the role of public education as a means to make life better on Earth. This is the goal that they've identified as the primary work of the Wertheim Family Foundation. Herbie and Nicole, we're honored that you've chosen to partner with us, and we're delighted to launch this brilliant new era in optometry and vision science. Thank you so much. Fiat looks, and go Bears.
Thank you so much, Chancellor Christ. You know, we're really blessed this evening with some amazing alumni and guests that have come, some from a long distance. But I did just want to give one shout out. You know, 7 of the deans of schools of optometry around the country are Berkeley alumni. And one of our best is just sitting here, just on my left, and I'd like to acknowledge Dr. Michael Twa, Dean of the University of Houston College of Optometry. As Carol told us, the Herbert Wertheim School of Optometry and Vision Science boasts the country's leading vision science research group. We are less than 1% of the faculty and produce nearly 5% of the campus funding. We boast the largest National Eye Institute NIH training grant, bigger than the other top 10 institutions combined, and we generate more research dollars than all the other schools and colleges of optometry combined. I'm delighted this evening to share with you a sampling of the excellence of our faculty and their research. First, I'd like to introduce Austin Rueda. Austin received his PhD in vision science and physics from the University of Waterloo in 1996. Go Canada. Completed a famously successful postdoctoral fellowship at the University of Rochester and joined the faculty at the University of Houston before joining UC Berkeley School of Optometry in 2005. Dr. Rueda has pioneered applications of adaptive optics and ophthalmoscopy, including building the first adaptive optics scanning laser ophthalmoscope, the mapping and tracking of individual human cones, and being part of the first team to use adaptive optics imaging to monitor the efficacy of treatment for retinal degeneration. Notable awards include the Distinguished Alumni Award from the University of Waterloo School of Optometry, the Glenn A. Fry Award from the American Academy of Optometry, the John S. Guggenheim Fellowship, an Alcon Research Institute Award, and a Leverhulme Visiting Professorship for a sabbatical to Oxford University in 2020 that was rudely interrupted by the pandemic, and we're sorry for that, Austin. Austin also received the first ever National Eye Institute NIH Audacious Goals Award in 2018. Dr. Austin Rueda.
Thank you, John. Chancellor Christ, Herbie and Nicole Wertheim. It's an absolute thrill to have a chance to speak here in front of you today, and of course all the other Berkeley alumni and current faculty and some students, I believe. So, and I'm a presbyope. I wear $4 reading glasses. I apologize for that. Okay, I'll explain the title as we get toward the end of the presentation. I lost my presentation. Here we go. Good. So our visual access to the world is achieved via a complex optical and neural system, ultimately leading to percepts that reflect the reality that's in front of us. And every step in that pathway imposes potential bottlenecks. The optics are fraught with imperfections, far from perfect, casting an upside-down and blurred image on the retina, and the retina is constantly moving, and it's comprised of 3 types of cones that are arranged in a seemingly haphazard way. The signals, though, from the photoreceptors are further processed by up to 200 million neurons in the retina. But then they get crammed into a wire, which is comprised of just 1 million axons connecting the eyeball to the brain. 1 megapixel, when I was young, that seemed like a lot, but 1 megapixel is really not that much. Finally, the brain processes the image, generates percepts that immediately, effortlessly, and accurately represent the world that we see. And it's this wonderful process that compels us all to, at least a number of us in our program, to study vision. So my specific compulsion has been to design and build and use advanced tools like the one shown here to study the early stages of this process in live humans. And our main technology is the adaptive optics scanning laser ophthalmoscope. It's a device that can record microscopic images of the retina in real time. It can also be used to track and deliver images to the retina. And the next few slides will summarize about 2 decades of work that led to the technology that we have today. So first of all, we use a technology called adaptive optics. And this is a set of optical technologies that can be used to measure and compensate for the optical imperfections of the eye. And when you correct for those optical imperfections, it's possible with an ophthalmoscope to turn it into a microscope to resolve individual cells in the back of a living human eye. Each one of the dots that you see is light scattered from a single cone photoreceptor. Second, we integrate that adaptive optics technology into a scanning system. A scanning system has benefits that go both ways. I can scan. Did I lose my slide here? I'm sorry. Here we go. A scanning system. A scanning system can not only be used to image the retina, but can be used to deliver images to the retina. So while I'm imaging a patient's retina, I can deliver an image to them, and what they see is simply a red box, which is the light from the scanner, imaging their retina and delivering the image. And then thirdly, through heroic efforts of people in my lab and collaborators over the years, we've managed to track the incessant eye motion in real time and deliver images to targeted locations. And here you see a letter E that is actually stabilized on the moving retina. So in the end, we've effectively hacked human vision, meaning that we can bypass normal visual processes and control activity in the retina in the ways that the retina or the optics were never designed to do. And hacking human vision in this way allows us to study human vision in health and disease in an unprecedented way. So human vision is actually very robust, and a patient with retinal degeneration can lose 50% of their cones before they present with a significant drop in their visual acuity. But with our system, we can bypass those properties and study structure and function of individual cells in patients with degenerative disease. And here, for example, I can measure and monitor the changes in the progression of the disease, learn more about the etiology of the disease by studying function of features as small as a single cone, asking questions about what is the function of that last cone at the edge of the lesion in this patient with a degenerative disease. Second, to better understand the role of eye motion for vision, we can simply compare acuity when an image is allowed to naturally move across the ever-moving retina or when it's stabilized on the retina. And we've recently shown in a couple of papers that this motion is not a problem for vision at all. In fact, we leverage this motion to improve our visual acuity. And then finally, we can stimulate large arrays of cones to play movies like this, not by having them look at a display, but by playing each individual cone directly over time. And when we do it right, we can in effect trick the eye into seeing colors or seeing objects that they've never seen before. And the project, which is called OzVision, has specific applications in the area of color vision. So for example, we aim to play the cones in a dichromat in a way that can simulate or elicit trichromatic vision, or imagine a trichromat adding a fourth cone class computationally and giving them tetrachromatic vision. We don't even know what that is, but we're keen to find out. None of this work is actually done by me. It's all done by lots of people over the years in my lab, and I thank them greatly for their time and effort. Thank you very much.
Thank you, Austin. Our next speaker, Dr. Otero Milan, joined Berkeley Optometry in July 2020 following a postdoctoral fellowship at Johns Hopkins University. And Herbie, I'll credit you here because we just managed to get him last year, and some of those hard negotiating skills come because Johns Hopkins did not want to lose this doctor, but we got him here. Jorge completed his Bachelor of Science degree in telecommunications engineering from the University of Vigo, Spain, and his PhD in neuroscience from the University of Vigo in collaboration with the Barrow Neurological Institute in Phoenix, Arizona. Jorge's research aims to understand how and why we move our eyes and how our eye movements affect the way we perceive the world. He also applies these findings to improve the use of eye movements in diagnosing patients with eye, brain, and ear disorders. Dr. Otero Milan is funded by the National Eye Institute of the NIH and the NSF, and I'm very proud to announce that last month he received a faculty award for excellence in postdoctoral mentoring, so congratulations, Jorge. We have great expectations for you and invite you up to come and give your talk.
Thank you, John, for the invitation and for the introduction, and thank everybody for being here. So I'm very excited today to talk about my passion, which is understanding eye movements and helping people by using them to diagnose them earlier and more accurately. So why do we want to use eye movements to diagnose people? First, because most of the brain is involved in generating eye movements. And not only that, but different parts of the brain control different types of eye movements. For example, some particular area may decide if we want to look up or down, left or right. Another area decides how we smoothly follow objects that move in front of us. And other areas may be related to head movements and generate these jerky motions of the eye. So by probing different types of movements, we can learn where lesions are in the brain very directly. Another advantage is that we can get, as Austin showed before, very precise measurements of eye movements easily without sticking electrodes in the brain. And they represent activity of the brain. As a mentor of mine used to say, like the ECG of the heart, you get activity of the brain directly from the eyes. Then, we are in an exciting time right now because technology is advancing very quickly. And there are many devices coming up that are doing eye tracking. So we can get eye movement recordings, for example, from devices that just look like regular glasses, like these ones, or from your phone, or your laptop, or many other devices that are around you. Now, at this time also, there is a great growth of artificial intelligence. So what does this mean for diagnosis? It means that we can get a lot of data, for example, many recordings of eye movements, and then an expert will label them with the right diagnosis. And you can feed that to a machine, shown here as a black box, and the machine will learn how to interpret those movements. And then you'll hope that later you can give a new recording that the machine has never seen, and it will provide the right diagnosis. But there are some things that can still be improved. For example, in this model, if something goes wrong, it's very hard to tell what in the machine caused the mistake. And also, if you have rare disorders, even if you understand them very well, it's hard to get enough data to train the machine. So I want to improve over these. And how? First, we can get better data, we can make data collection more accessible, and then we can make the machines smarter. And these will be some examples of my work. So first, all of these devices only record eye movements of the eye left to right and up and down. But I've developed software that will record eye movements like the one shown here around the line of sight. And these movements are important for diagnosis of vertigo and other disorders like strabismus, for example. And now there are several studies using the technology I developed for these tests. Then, with all these new devices, we can get eye movement testing farther into the field. Right now, there are only expensive devices that very few institutions can afford. So with the new technology, we can push the same tests in all clinics and eventually to the home of the patients. So we did a study where we implemented the same test with the clinical expensive device and with just a regular smartphone, and we got the same data from both tests. And finally, we can make the machines smarter. And the idea here is to be able to make a model that simulates how the brain moves the eyes. And by doing those simulations, we can also simulate what goes wrong. So we can change different parts of the model and see what the eye movements look like. For example, there was a complicated case that even one of the biggest experts of the field couldn't make up. The eye of the patient sometimes was jerking one way, sometimes the other way, and sometimes it was just still. But then by using our model, we could just change two positions that represented some areas of the cerebellum to generate a simulation that matched exactly what the patient was doing. And we could confirm where the lesions were. So I hope that with these improvements, we can help diagnose many patients with dizziness and vertigo, amblyopia and strabismus, Parkinson's, ataxia, et cetera, et cetera. So thank you all for being here, and thanks to my lab and all the mentors that helped me get here.
Thank you, Jorge. Hopefully you can see why we're so excited about Jorge joining us. Next, I'd like to introduce Dr. Teresa Patisserie. Teresa received her optometry and PhD degrees from the University of Melbourne, where she subsequently completed 2 years of postdoctoral work. She then transitioned to Oregon Health and Science University as a research assistant professor and was appointed at UC Berkeley School of Optometry as an assistant professor in 2016. Dr. Patisserie is already a star within our faculty, an innovative and popular teacher, and a retinal physiologist of international repute. Recent awards include the Faculty Award for Outstanding Mentorship of Graduate Student Instructors in 2019 and a Hellman Fellows Fund Award. Her research is funded by the National Eye Institute of the NIH, the Knights Templar Eye Foundation, and she has a Schaefer grant from the Glaucoma Research Foundation. That's my reminder to take my medication. There you go. Sorry, Teresa. A Schaefer grant from the Glaucoma Research Foundation. And I'm delighted to say that earlier this month, it was announced that Dr. Patisserie has received the highly prestigious Audacious Goals Award from National Institutes of Health. Please help me welcome Dr. Teresa Patisserie.
Thank you very much, Dean Flanagan. I hope you take your medication. And good evening, everyone. So, like many of you here this evening, I started my career in optometry school. And one of my strongest memories of that time is of a patient I saw in the low vision clinic. He and I had a lot in common. We were the same age, in our early 20s at the time. He was planning a trip to Nepal to see the Himalayas, and I had just returned from working in an eye hospital there. He then explained that this trip was really time critical for him because he was progressively losing his vision from an inherited form of incurable blindness called retinitis pigmentosa. In that moment, I wished I had something hopeful to say about his condition. It's been 2 decades since then, and though we still don't have widely available treatments for patients like mine, the future looks a lot brighter. My lab here at Berkeley studies the neural circuits of the retina and how they're altered in diseases like retinitis pigmentosa and macular degeneration. These conditions cause the progressive degeneration of the photoreceptors, the light-sensitive neurons of the retina, and this is what leads to blindness. But the remaining neurons of the retina remain relatively intact, including the ganglion cells, which send visual signals from the eye to the brain. And so many groups, including mine, are interested in how we might leverage these remaining neurons to restore vision in patients with photoreceptor degeneration. So how might this be achieved? One approach is to generate new photoreceptors from stem cells and to transplant those into the degenerate retina. Another approach that was just tested in the first human patient earlier this year is to introduce light-sensitive proteins into some of the remaining neurons, like the ganglion cells. The success of therapies like these relies on us understanding both the structure and function of the retina in the normal state and after the photoreceptors die. In my lab, we use advanced optical imaging and electrophysiological tools to study retinal function in health and disease. The retina is an amazing model system because you can remove it from the eye and keep it alive and light responsive in a dish under a microscope so that we can study neural function on the cellular scale. Here, we're watching a recording from a normal retina where we've loaded a fluorescent indicator into the ganglion cells so that we can see when they're active. I've highlighted a couple of these oval profiles, and all of these roundish profiles you see are individual cells. Now, in a normal healthy retina, when we stimulate this sample with light, we can see that the ganglion cells light up. And this is because the photoreceptors detect the signal and pass it down to the ganglion cells. Now, you might imagine that in a blind retina, when the photoreceptors have degenerated, that the ganglion cells might simply fall silent because they've lost their photoreceptor input. But we and other groups have shown that this is not what happens. The ganglion cells, I've pointed one out here for you to watch, instead become spontaneously hyperactive. They start responding even when there's no light stimulus. This aberrant spontaneous activity may interfere with efforts towards vision restoration because it creates a lot of noise in the signal sent from the eye to the brain. It would be a bit like me giving this talk if all of you were talking at the same time. The useful signal simply gets lost in the noise. The scientists in my lab are trying to understand why this aberrant activity develops, and we've recently identified a drug that might help suppress this activity to improve the quality of vision restoration. Finally, our ultimate goal is to translate what we've learned from studying retinas in a dish to improve therapies for human patients. Towards this end, my lab has recently been funded, together with my collaborators, to test whether stem cell-derived photoreceptors can restore vision in a large animal model of macular degeneration. This study is one of the first of its kind, and my lab will use our expertise in high-resolution structural imaging to determine whether stem cell-derived photoreceptors can integrate and connect with the host retina, and if they can't, to try and understand what barriers we might need to overcome. When I think back to my patient now, I know we still have a long way to go, but with the advances over the past 2 decades, it's my hope that in my lifetime, that patients like mine and the many others that are suffering from vision loss might once again be able to see the light. Thank you very much.
Oh my goodness, I think you can see why our students love being taught by Teresa so much. And thank you to our 3 speakers who really had the job of representing our brilliant faculty in this occasion, celebrating the brilliance of Berkeley Optometry. There's another thing I'd like to acknowledge, that Teresa is the latest in our tradition and long line of famous Australians who've come to the faculty. And of course, we lost Tony Adams, one of the greatest of them all. And I didn't want to go tonight without acknowledging that we lost Tony just recently. But I would like to acknowledge our old mate Ian Bailey over there, who has come along to join us. Finally, before we head upstairs and enjoy some food together, I would like to introduce you all to our benefactor, Dr. Herbert Wertheim. Herbie, if you'd like to come up and just say a few words, but do remember that the sunset's happening soon, so you
Bit of a showman, but let me see if I can. I actually wrote a few things here that I thought were important that I don't forget this time. Wow, this is bigger than I ever thought it was going to be. I can't tell you how important it was to deal with this lady here. She came down to Rancho Santa Fe 4 years ago or whatever it is, and we talked about the School of Optometry. And she came with the dean, and we talked, and we had lunch and this and that, and they thought for sure they were going to have a sure thing. Well, 4 years later, after dealing with our friends at Houston, Alabama, and a few other situations, we took the time to decide where we thought we could do the most change in optometry. Because as an optometrist, I graduated in '67, and I started optometry, if you can believe that, 3 or 4 years before that. So it makes me almost 60 years thinking about eyes. It's a long time. I got my first interest in eyes when I was a young engineer at NASA in manned spaceflight with John Glenn and the other astronauts. They were crazier than hell, except for John. I mean, and we danced at night, we drank at night, we did everything, and I learned about instrumentation as far as the eye was concerned. We were tracking nystagmoid movements, if you can believe such a thing, to be able to find out what was happening to the body. And as a result of that, later on, when I was doing some research, I used a nystagmoid system that I had built to be able to check for dyslexia. And we came up with 4 or 5 different colors that we thought quieted the sympathetic and parasympathetic nervous system. So again, you're on the right track. Thank you for that. Cheryl Anderson is here. Cheryl, are you here? Would you please stand up, Cheryl? I think Cheryl's here. Dean Anderson? Well, apparently she's left. She was here. Oh, here she is. Here. Another story. That was a 5-year thing. Her boss, David Brenner, and I became friends about almost now 7-8 years ago. And we were together, and I kept talking about public health, and I thought it was the most important thing that we could do in America. And it took us a number of years to put things together, like 5 years, and your contract was 92 pages. I think theirs was 96 pages. We had a 10-year roadmap as to what we were going to try to do. And Cheryl, thank you. She now has almost 1,000 students now, Cheryl, in your first year or second year, and a faculty of over 100, and one of the largest grants at UCSD. So thank you very much, Cheryl, for coming today. I wanted to recognize you and the excellent people that they do it. I'd like to recognize my daughter, Vanessa, who's on the board of Rady Children's Hospital, who, what can I say, she's our wonder child. She was born 2 pounds, 10 ounces. She had all the things that people who are born with 2 pounds, 10 ounces do, strabismus, all kinds of nystagmus, amblyopia, you name it. Well, she now is somewhat emmetropic. She's had 2 surgeries, one by a guy who didn't know what the hell he was doing, and our good friend John Flynn, who most of us, I don't know if you ever knew John, but John and I did research at Bascom Palmer for almost 10 years. So Vanessa has her MBA, she has her, what can I say, nursing degree, and she has her PhD now in nursing, and she's giving back. There's a young lady who says, I made it, and I want to give back, and she's on the board of Rady Children's Hospital. Well, I want to recognize her. And I don't know how to really appreciate my wife. I mean, I shouldn't be up here telling you how good my life has been, but it's been extraordinary. My wife, Nicole, French, She married me, and we lived on our houseboat. I cooked her a hamburger the first date, and she never eats hamburgers, but she thought my hamburger was pretty good. We got married a few months later, had a baby, lived on a houseboat, and she has been everything a husband could ask for or a researcher could ask for. She allowed me to sleep on my research laboratory floor in my sleeping bag many times as I built our company. She allowed me to go to the medical school where I taught for many years in the physics department to sleep in a cot, and she's allowed me to be everything I could be. So without my wonderful wife, Nicole, I wouldn't be who I am today. So thank you, Nicole, for allowing me. Some of you were at the dinner last night, and you heard me say, optometry, and I'm going to say this loud and clear, and I'm going to stamp my foot. Optometry is America's godsend for the prevention of blindness. We are it. We've not said it long enough and loud enough. There are 10 times as many of us as there are ophthalmology. We are there as in almost every neighborhood in America. We are there to do good. So not only do we discover a problem, diagnose the problem, and remediate the problem. Those are the 3 things we do every single day. And we need to be taken seriously about the health care that we can achieve in America. We are the first line of defense against blindness and incapacitation in the workplace in America. So I want all of you to think about that in a very, very serious way and think about how we are the lifeblood of being able to prevent blindness. One of the reasons we got involved with Berkeley and with Houston and with Alabama and some of the others is because of our love for children's vision. As a young optometrist, I called myself a vision neurologist because I dealt with amblyopia, I dealt with vision problems of one type or another, and most of them were in children, although some were in adults. We are, again, the first line of defense to identify these young people who need our help, not just for acuity, but for performance. Performance is what we would like to have, where someone can read longer, better, with better comprehension, and feel good about doing it. Because our prisons are filled with people who can't read. I mean, if you can't read in society, what in the heck are you going to do? You're going to rob a bank, you're going to be a mugger, you're going to be somebody who's not doing something that has to do with a productive thing. So again, we are again the first line of defense. We need to find these people, these young people, and help them achieve good vision and good performance. So we propose with the dean, who I love. I mean, he's wonderful. I fought with him a little bit. I'm going to tell you, we fought. And we came to a meeting of the minds, and the university bent over like crazy. I can't tell you. They really performed. Now, we're going to have a model children's clinic dealing with children here at the college, and also at Rady Children's Hospital as we get it done, and also hopefully at San Francisco. I had a meeting with the president of the UC system across the table. He's an ophthalmologist. I didn't know if you knew that. And I got kind of a handshake. It wasn't what I call a firm handshake, but pretty good handshake, that we're going to be able to get the assistance of him and also the chief ophthalmologist at the clinic at San Francisco. So let that be our first step. Let us optometrists think about who we are. We are the first line of defense against blindness in America. Thank you for allowing me to speak.